Hello, everybody. So this is room 3 of the virtual ICM. And actually, we're going to participate in an on-site event in Copenhagen. Our first speaker today is Robert Young from the Current Institute at the NYU. And the title of the talk is Composing and Decomposing Functions and Surfaces. Robert, I give you the floor.
Thanks for the introduction, and thanks to the local organizers and to the global organizers. It's an honor to be here. So today I want to talk about how to build complicated objects out of simple ones, and conversely, how to take complicated objects and decompose them into simple objects. Just like you can take a bunch of triangles and glue them together to make the Koch snowflake, you can take the Koch snowflake and you can decompose it into its component triangles. So the motivation for this talk is basically this question: what's the most complex surface? The trouble is that the most complex surface is probably too complicated to really work with. You expect the most complex surface to be more complicated than the most complicated graph. The most complicated graphs are already too complicated to draw, too complicated to embed in Euclidean space. And so let's make it a little easier for ourselves. Let's look for the most complex surface in Rn, because then we at least have a chance of being able to draw it, of being able to visualize it, of being able to do geometry on it. But this is even still a little bit too hard, because if you have a surface in Rn, you can always make it more complex. You can start with the cube. You can drill holes in the cube to get the first step of the construction of the Menger sponge. And then you can repeat the process. You can drill more holes and more holes and more holes to get closer and closer to the Menger sponge. And really the surfaces, the steps in this construction are getting more and more complicated. So we expect the most complex surface in Rn to again be sort of unboundedly complex. And so let's, the construction of the Menger sponge, on the other hand, I mean, you're adding more complexity, but every time you go another step, you're also adding more area. So let's ask instead, sort of, what's the most complex surface in Rn of a given area? How much complexity can you get for a fixed amount of area? How much complexity can you get per area? And this is the question that we can actually make some headway on. So this is the question that I want to try to address today. And so there are roughly 3 parts to the talk. I'm going to start by talking about Lipschitz functions and asking what the most complicated Lipschitz function is. Then I want to move on to surfaces and measure and talk about topological complexity, especially nonorientability. And then I want to talk about how to apply some of these ideas to metric geometry, and especially something called the Heisenberg group. Okay, so let's start with a warm-up. Let's look at Lipschitz functions. So remember that a function is L Lipschitz if f of x minus f of y is at most L times the distance between x and y for all x and y in the domain. And then we can ask, what's the most complicated one Lipschitz function? Well, it probably looks like something like this. I mean, this is this is a fairly complicated function. It's got a lot of structure to it. It looks different at different scales. If you picked any point on this and zoomed in, you would probably get a different picture. So this particular example is constructed very similarly to the Weierstrass function. You take, say, a wave, and then you add to that another wave of, say, twice the frequency, half the amplitude, and then another wave with higher frequency, lower amplitude, so on and so forth. And so maybe each of these individual pieces, maybe each of these has a derivative of norm. Let's call this beta 1, beta 2, beta 3, and so on. And each individual beta has derivative on the order of 1, say. Now this isn't quite the Weierstrass construction here, because the Weierstrass function is an infinite sum. If you try to do an infinite sum, you won't get a Lipschitz function, because what can happen is that there are going to be points where these waves all have the same slope. They have a positive slope here, positive slope here, positive slope here. And then when you add it all together, you get a very steeply sloped curve. You start to lose the Lipschitz condition because your derivative is getting too large. And so, after n steps, the maximum derivative is going to be on the order of n. But on average, it should be much smaller. On average, and if we pick a generic point, say like so, then we're going to have some points where you have negative derivatives, some points where you have positive derivatives, some points where you have negative derivatives. You essentially have, for each term in this sum, you get a random number between -1 and 1. And we know that a random number between, that if you add n random numbers between -1 and 1, you're typically going to get something on the order of root n. So the maximum may be on the order of n, but the average is going to be much smaller. It's going to be on the order of root n. So you can you can construct a function which is, say, L Lipschitz by adding together about L waves. But if you add together about L squared waves, then you'll get a function which is not necessarily L Lipschitz, but it's mostly L Lipschitz. It's L Lipschitz at most points. So just to write this down, just to formalize this a little bit, we can construct the functions like this by taking some epsilon greater than 0, choosing a bunch of scales R1 through Rk, which are sufficiently separated, getting smaller sufficiently quickly. And then for each scale, we can define a wave beta I with wavelength Ri, amplitude epsilon Ri, so that the slope of this wave is between negative epsilon and epsilon. And then we can add these together to form F. Then, well, again, we want to know what happens to the derivative of F when we do this. What happens to the Lipschitz constant of F when we do this? Well, because the length scales are getting smaller and smaller as we go, we expect that the derivatives of the beta i's are mostly orthogonal. We expect that the square of the norm of F prime is roughly the sum of the squares of the norms of the beta i's. Remember, the beta i's have derivatives between negative epsilon and epsilon. And so the norm of F prime squared is going to be on the order of k times epsilon squared. And as long as k epsilon squared is sufficiently small, then F is going to be mostly 1 Lipschitz. The derivative of F is going to be between -1 and 1 at the vast majority of points. And so what this gives you, if you take k as large as possible, if you take k on the order of epsilon to the -2, you end up with a 1 Lipschitz function which has bumps of scale epsilon at roughly epsilon to the -2 different scales. And this is sort of the bumpiest Lipschitz function possible. And so it's arguably one of the most complex Lipschitz functions you can construct. Actually, I guess I should justify that a little bit because, well, why is this sharp? Well, if we take an arbitrary 1 Lipschitz function, we can break it down. If we take an arbitrary 1 Lipschitz function, we can break it down into, the contributions from different scales. We can take a sequence of approximations. I'm going to start. My first approximation is just going to be a line connecting the endpoints of the function. And then I can construct further approximations by taking the midpoint and just drawing piecewise linear functions that connect the endpoints of the curve to the midpoint. And then repeat at a smaller scale, take midpoints of those intervals, connect them by straight lines, take midpoints of those intervals, connect them by straight lines, and so on and so forth. Let's call these approximations f sub I, and then we can use these f sub I to measure how bumpy the function is, how much the function changes when we approximate at one scale versus the next. So we'll define g sub I to be the derivative of the difference f sub I plus 1 minus f sub I. This is going to, this measures how much the slope changes when you go from one scale to the next. This roughly measures how bumpy the function is at a given scale. And furthermore, because of the way we've constructed these, the functions are piecewise linear, the derivatives are piecewise constant, and the g sub i's are going to be actually orthogonal to one another. And so the square of the norm of f prime is equal to the sum of the squares of the norms of the g sub i's. And because f prime is between -1 and 1, because the function is 1 Lipschitz, this norm has to be at most 1. The sum of the norms of the g sub i's has to be at most 1. And so you can't have more than epsilon to the -2 of the g sub i's that are bigger than epsilon. The function can only be epsilon bumpy at about epsilon squared different scales. So this Weierstrass construction is more or less the best we can do, the most complex Lipschitz function we can construct. And so this is an important idea in a lot of analysis. It shows up in Fourier series, in Littlewood-Paley theory, in Doran-Soros inequality on approximating Lipschitz functions by affine functions, in the Jones traveling salesman problem, in David and Sam's work on uniform rectifiability, in a lot of places in analysis. And today what I want to do is I want to try to apply similar ideas in geometry. So how do we do that? How do we go from Lipschitz functions to surfaces in Rn? Well, on one hand, if you have a Lipschitz function, say a Lipschitz function from Rm to Rn, then its graph is an m-dimensional surface in Rm plus n. So Lipschitz functions produce surfaces. On the other hand, a general surface in Rn, a general k-dimensional surface in Rn, can be much more complicated than the graph of a Lipschitz function because it can have some topological complexity to it. So how do we bound the topological complexity of a surface, or even how do we measure the topological complexity of a surface? In general, I don't have a good answer to that, but I can tell you about one particular aspect of topological complexity, which is nonorientability. So how do we measure nonorientability? Well, what do I mean by that? What does it mean to measure nonorientability? Basically, what I mean is this. Say I have a surface in Rn. So I'm going to draw, say, a two-dimensional surface in R4 because I want it to be non-orientable. So I'm going to take a plane, I'm going to cut out two disks, and I'm going to connect those two disks by a cylinder, and I'll give the cylinder a half twist in the middle to make it non-orientable. This is called a cross handle. So this is non-orientable. What I want to do is I want to measure how non-orientable it is. I want to be able to say, for instance, that if I take another surface, another plane, and I do this to it, if I add two cross handles, this ought to be more non-orientable than the first one. If I take another plane and I take out two tiny little disks, this ought to be less non-orientable. And so let's formalize that intuition. So one way to formalize this uses language of chains and cycles. Let's let D be less than N. D is the dimension of the surface, N is the dimension of the ambient space. And let's let K be a D cycle with coefficients in Z mod 2. So this is essentially the fundamental class of some possibly non-orientable D manifold in Rn. So we have a Klein bottle there. If the surface is orientable, then it has an orientation. Then its orientation is the fundamental class, sorry, its orientation gives rise to a fundamental class, which is a cycle with coefficients in the integers with exactly the same support. So we can express orientability in terms of lifting the fundamental class with coefficients in Z mod 2 to some fundamental class with coefficients in Z. Now, the Klein bottle is non-orientable. So its fundamental class doesn't lift to a cycle with coefficients in Z, but we can produce what I'm going to call a pseudo-orientation. There is an integral cycle with bigger support than the Klein bottle, which is congruent to the fundamental class of the Klein bottle. In this case, what we can do is we can take, say, the neck of the Klein bottle. If we cut the neck of the Klein bottle, we get a cylinder. If you cap off both ends of the cylinder, you have a sphere, and the sphere is certainly orientable. So what is the fundamental class of that sphere? Well, it's the surface of the Klein bottle with a certain orientation, plus two disks, one at each end of the cylinder. And because of the twist in the Klein bottle, those two disks have the same orientation. So you have the surface of the Klein bottle with multiplicity 1, and then you have that disk with multiplicity 2. It's congruent mod 2 to the fundamental class of the Klein bottle, but the area is bigger. Specifically, the area is bigger by exactly the area of those two disks. More generally, we can do the same thing for arbitrary D cycles. It's easier to define this in the context of cellular D cycles. So we'll take the unit grid in Rn. We'll look at D-dimensional cycles in that unit grid. And then for any D-dimensional cycle with Z2 coefficients, we define the non-orientability of that cycle to be the smallest area of a pseudo-orientation of that cycle, the smallest area of a cycle with integer coefficients, which is congruent mod 2 to that cycle. And so in particular, if your original cycle is orientable, then it's easy enough to lift by choosing an orientation. The non-orientability is equal to the area. And furthermore, this quantity is subadditive. If you have two cycles A and B, and you have a lift of A and a lift of B, then the sum of those lifts is a lift of A plus B. So the non-orientability of A plus B is at most the non-orientability of A plus the non-orientability of B. And this more or less measures sort of how much editing you need to do to a cycle in order to make it orientable. And in the case of these surfaces, what this measures is basically how much area it takes to cut this cross handle, how much area it takes to cut these two cross handles, or how much area it takes to cut this little cross handle. It's a way of measuring non-orientability. And so we can ask, okay, what's the most non-orientable surface? That's not quite the right question because, if you take a surface and you scale it up, the area is going to increase and the non-orientability is going to increase at the same rate. So really what we want to know is how large can that ratio be? How much non-orientability can you produce for a given area? And so, well, let's try something. Let's try one example. So what we can do is we can start with a cube. Say we have a cube of side length r. And then we can add, this is orientable, so we're going to add some cross handles to make it non-orientable. Let's start by adding cross handles on each face. Eventually, we're going to run out of room on the faces. We can't add any more. So we'll add cross handles at a smaller scale. And then a smaller scale. And then a smaller scale. And so on and so forth. So more formally, we pick a cube of side length r. This is going to be, a two-dimensional surface in R4 again. We're going to choose a sequence of scales between r and 1, call them R1 through Rk. And then for each of these scales, we're going to add cross handles of that scale to the surface of the cube. So the original cube has area r squared. Each of these cross handles takes up about ri squared area on the cube. And so we'll get about r squared over ri squared cross handles of each scale. And this is a surface which should be very non-orientable, because in order to orient this, you have to cut all the cross handles at all the different scales. How non-orientable? Well, we can calculate that it takes about ri square area to cut each of the cross handles of scale ri. There are r squared over ri squared of these handles. And so you get about r squared non-orientability from each scale, k different scales, so you get kr squared total. So the non-orientability is growing as we repeat this process, as we add more scales of cross handles to this surface. But the ratio of the non-orientability to the area stays bounded, because every time we add a cross handle, it adds to the area. Adding the cross handles at scale ri adds about r squared to the area of the surface. And so you have maybe the area of the original cube plus the area coming from each of the k scales. You have roughly k plus 1 r squared total area. And the ratio between the non-orientability and the area stays bounded. So you may ask, and there are lots of ways to construct non-orientable surfaces. There are lots of non-orientable surfaces that are embedded in Rn. What are other ways to construct non-orientable surfaces? What if you, instead of adding cross handles, maybe you cut out a disk and glue in a Mobius strip, maybe you add a cross cap, or maybe you start with some different object, or maybe you construct in some different way. It turns out that no matter what you do, you can't add non-orientability without also adding area. That no matter what you do, the ratio between the non-orientability and the area stays bounded. So for every cellular cycle A, the non-orientability of A is bounded by a constant times its area. This is stated for cellular cycles, but we can also state something similar for non-cellular cycles. If we have some smooth surface, we can approximate it by cellular surfaces, and then down the non-orientability of the smooth surface in terms of the cellular surfaces. And this has some applications in geometric measure theory. So for instance, some of the I don't want to go into too many of the applications because a lot of them take some terminology to state, but one that's relatively simple to state is this, that if you have an area minimizing surface with a given boundary, call the boundary T, then any area minimizing surface with twice that boundary 2T, has to have area at least epsilon times the area of the original surface. And this seems a little weird because you would normally expect that if you have a minimal surface with boundary T, and then you double the boundary, then the area should double. But there are some examples due to L.C. Young, due to Brian White, due to Frank Morgan, where you have a minimal surface with a given boundary, you double that boundary and the surface changes. So the minimal filling of twice the boundary only has about 1.7 times the area of the original. What this corollary says is that if you double the boundary, the area can't go to 0, which again is much less than what you would expect. I mean, you would expect at the very minimum that if you double the boundary, the area of the minimal surface increases. But we don't know that. This is what we know. The area doesn't go to 0. But yeah, so how do we prove this theorem? How do we prove this bound on the non-orientability? The basic idea is to take an arbitrary surface and decompose it. So if we take this, for instance, this cube with all the handles attached, we can write this roughly as a sum of orientable pieces. We can start with the original cube. Then what did we do? We added cross handles of some scale to each of the sides. How can we express that? Well, that means that we deleted 2 circles and we added a cylinder. We can write that as taking a cylinder with half a twist and capping off the boundary. This is a sphere. This is an orientable cycle. This is a cycle with integer coefficients. And if we add it to the cube, what happens? Well, this disk overlaps with this piece of the cube. This disk overlaps with this piece of the cube, but we're working mod 2. So if you have 2 copies of something, they cancel out. And what we end up with is a cube with 2 disks removed and 1 cylinder glued on. We end up with a cube with a cross handle. So the whole first stage of this construction can be written as writing the cube plus a sum of spheres, of orientable spheres. And likewise, the whole second stage of this construction is adding a bunch of smaller handles and and so on and so forth. We can write all the stages of this construction as adding a bunch of spheres to this cube, mod 2. And so because all of these spheres are orientable, the non-orientability of each of these spheres is equal to its area. And so the non-orientability of the whole cube is bounded by the total area of all of these spheres, of the original cube plus all of these spheres. And that gives us the bounds that we saw before. But how do we do this in general? How do we say something about a general surface, an arbitrary surface? Well, what we're going to do is a similar sort of decomposition. What we're going to do is we're going to apply a greedy algorithm to decompose an arbitrary surface into not necessarily orientable pieces, but at least into simpler pieces. And each step of the decomposition, we're going to try to decrease the area of our surface. So say we start with some, let's say our surface looks like this. Say our surface is just a sort of snake shaped. What we're going to do is we're going to call this surface M. Let M1 be equal to M because we're going to proceed iteratively. And at each stage, what we're going to do is we're going to find some ball, B1, where there's a deformation that shrinks the area of the surface. In this case, we can take the head of the snake and we can deform do a homotopy inside the ball to just get something smaller. That deformed surface, we're going to call that M2. And then we're going to define the first piece of our decomposition to be the difference between the original surface and the deformation. So in this case, our original surface had that tip there. We've cut that off, we've deformed that away. And so the difference between those is going to be basically a sphere coming from the head of the snake. And then we repeat. We find another ball where there's a deformation that reduces the size of the surface. And then we call that M3. And then the difference is going to be the next piece of our decomposition. And so on and so forth. We find balls on which we can decrease the area of the surface. And then we use those balls to construct pieces of this decomposition. One term for this is that at each stage, we're going to find some ball B sub I where M sub I fails to be a quasi-minimizer on D sub I because there's this deformation that shrinks the surface. So when do we stop? Well, eventually on the snake, we're going to get to the point where we just have the tip of the tail. And at that point, well, the only thing that's left to do, the only deformation that's left to do to reduce the volume, to reduce the area, is to just take that tip there and just shrink it down to a point. Eventually, our M sub I, eventually one of our surfaces ends up being 0. And at that point, we have a decomposition of our original cycle into a sum of smaller cycles. So this is a picture of how this works in the case of this sort of snake surface, where and what's special about this surface is that it's very thin. It's very skinny. If I take a ball around one of the ends of the snake, the surface doesn't take up very much of that ball. So we get a decomposition like this that just cuts it into cylinders. In general, though, this decomposition also works for more complicated surfaces. If we have something more complicated, say we have some surface that looks like, this. We have, maybe it's mostly flat, but then it's got some piece which is very complex. This works pretty well here too, because what happens is we look for a ball on which we can shrink the surface. In this ball, we can take the surface and we can just project it down to the line. That decreases the area by a lot, so that gives us a piece of the decomposition. And this is what happens in the cube, in this cube with all the handles on it. Because what do we have here? Well, we can take, say we have a ball that contains one of these faces. If we have a ball that contains a lot of cross handles, then we have a deformation which just projects that face to the original face of the cube, and it decreases the area substantially. And that's really the one thing to be aware of here, though, is that, remember, we're always looking for the smallest ball on which the surface fails to be a quasi-minimizer. We're always looking for the smallest ball where we can have a deformation like this. So we're not going to start with the whole face. We're going to start with some small ball that still contains a lot of cross handles, and then project that down, giving us a piece of the decomposition, which basically, looks like a sum of small spheres. We then repeat that. We find another ball, another small ball with a lot of cross handles, and another small ball and another small ball. Eventually, we're going to get rid of all the smallest cross handles, and then we'll move up to the next scale up. We'll move up to larger balls that still contain a lot of cross handles and get terms in the decomposition that look like these larger spheres. Until eventually, we run out of cross handles entirely. All that's left is our original cube. And at that point, the best way to shrink the volume is to just take a ball containing the entire cube, shrink the cube to a point, and that gives us the last term in our decomposition, just the original cube. So this decomposition works in a variety of circumstances. And furthermore, it has 3 properties that I want to make a note of. First, because we started with a cellular surface, the area of the original step is an integer. And if we do this carefully, we can make sure that all the intermediate steps are integers too. So the areas form a decreasing sequence of integers. And so eventually, this process has to terminate. Furthermore, because of the way we're doing this, because each stage decreases the area, Well, each stage decreases the area, and the amount that the area decreases is always going to be comparable to the area of the piece we just added to the decomposition, to the area of each new piece in the decomposition. So that means that the total area of all the pieces in the decomposition is going to be comparable to the amount that the area decreased throughout this entire process is going to be comparable to the area of the original surface. So this is an efficient decomposition in the sense that the total area of the pieces is comparable to the area of the original. And then finally, and this is a little bit subtle, because we're always taking the smallest ball on which the surface can be deformed to something smaller, because we're always taking the smallest ball on which m sub I is not a quasi-minimizer, that means that m sub I is a quasi-minimizer on all the smaller balls. And this is important because being a quasi-minimizer on all those smaller balls lets us bound the complexity of all the pieces in this decomposition. There's a theorem of de Wied and Semmes that a quasi-minimizer in Rn is uniformly rectifiable. The definition of uniform rectifiability is a little bit too complicated for me to get into in a short talk like this, but the rough idea is that a surface is uniformly rectifiable if you can approximate it by not too many Lipschitz graphs. So for instance, if you have a square, that's uniformly rectifiable. You can approximate it by 4 Lipschitz graphs, 1 for each face. And then if you pick a random point on the square and draw a ball around that point, you probably didn't hit one of the corners. And if you didn't hit one of the corners, then you had then the square is exactly equal to that graph in that ball. So on most balls, at most radii around most points, the square can be approximated by one of these 4 Lipschitz graphs. You're allowed to have, this is one of the simplest uniformly rectifiable surfaces. You can have more complicated surfaces. So for instance, we've been talking about taking cubes and adding handles to them. You could do the same thing here. You could add, say, a handle like this, and a handle like this, and a handle like this, and so on and so forth, getting smaller. You just can't cover the whole surface by these handles, because if we just have a few handles, then we can say, okay, let's add a graph like this, and a graph like this, and a graph like this, and like this, and so on and so forth. And again, the surface is going to be approximated by these graphs on most balls. But there's a nice quantitative bound. There aren't too many of these extra Lipschitz graphs here because you only have so many handles. So yeah, so the pieces in this decomposition, if you do this decomposition carefully, you can make them all uniformly rectifiable, and that gives you a bound on their complexity. And this leads to the proof of the theorem, because we can take an arbitrary surface and we can break it down into uniformly rectifiable pieces efficiently. And then those pieces aren't very complicated in themselves. Any mod 2 D cycle with uniformly rectifiable support has a uniform bound on the ratio between its area and its non-orientability. And then the inequality follows. We have some original surface M. We break it down into these uniformly rectifiable pieces A sub I. The non-orientability of M is bounded by the total non-orientability of the pieces. The non-orientability of the pieces is bounded by their area, but the decomposition is efficient enough that the total area of the pieces is mostly constant times area of the original surface. And so you can't add extra non-orientability without also adding extra area. More generally, this gives us a rough answer to our original question. This gives us a rough answer to this question of what's the most complicated surface in Rn of a given area. Because this tells you that no matter what surface you have, you can decompose it into uniformly rectifiable pieces of roughly the same total area. And then each of those uniformly rectifiable pieces can be described in terms of Lipschitz graphs of total area on the approximately A. So if you understand Lipschitz graphs, you can roughly understand the uniformly rectifiable pieces, and then you can roughly understand the original surface. The original surface isn't too much more complicated than a collection of Lipschitz graphs of total area on the order of A. Okay. So this is a project I worked on several years ago. Since then, one of the things I've been working on is a project with Asaf Naor to try to apply this in other spaces, to try to understand what other spaces have this property, that the most complex surfaces are still not that much more complicated than Lipschitz graphs. And one of those surfaces is something called the Heisenberg group. So the Heisenberg group is a nilpotent Lie group. It's a 2k plus 1 dimensional nilpotent Lie group. You can write it as a matrix group with k plus 2 by k plus 2 matrices with ones along the diagonal. The top row has coefficients x1 through xk and z, and the rightmost column has coefficients y1 through yk and z. And that's a nilpotent Lie group. It contains a lattice where you force all the coefficients to be integers. And the lattice is generated by generators x1 through xk, y1 through yk, and z, so that the commutator of xi and yi is z, and all the other pairs commute. And the lattice, when k equals 3, the lattice looks like this. We have the lattice points in R3. And if you multiply by x, the x coordinate increases by 1. If you multiply by z, the z coordinate increases by 1. If you multiply by y, the y coordinate increases by 1, and the z coordinate changes according to the x coordinate. This has the property, one way to think about this space is this is a space where if you start at a point and you go left one step and then back one step and then right one step and then forward one step, you end up one step above where you started. If you go left 2 steps, back 2 steps, right 2 steps, and then forward 2 steps, you end up 1 step above where you started, or 4 steps above where you started. The group is non-commutative, and that has a strong effect on its geometry. In particular, it makes it hard to embed the Heisenberg group into spaces like Banach spaces where you have a lot of commutativity. The first theorem to this effect was a theorem of Ponceau and Semmes, who showed that there's no bi-Lipschitz embedding from the Heisenberg group into Rn. And this is really based on the non-commutativity of the Heisenberg group and the differentiability of Lipschitz curves in Rn. Because one way to prove this is to say, okay, you have your Heisenberg group, you have a Lipschitz map to Rn. The lines in the previous picture, the horizontal lines in this picture, have to get mapped to curves in Rn, which are almost everywhere differentiable, which are close to straight lines on a lot of balls. And you can't have this structure, you can't make this non-commutative structure out of straight lines in Rn. In Rn, if you go left and then back and then right and then forward, you end up back where you started. In the Heisenberg group, if you go left, back, right, and then forward, you end up above where you started. And that difference between non-commutativity and commutativity leads to the lack of a bi-Lipschitz embedding. This same argument, or an argument like it, works in a lot of Banach spaces. It works in Banach spaces with the Radon-Nikodym property because those have the differentiability property you need in order to do that. But it doesn't work in spaces without the Radon-Nikodym property. More recently, Tiger and Kleiner extended this to one such space, to L1. They showed there's no bi-Lipschitz embedding from the Heisenberg group to L1. But what does this have to do with surfaces and the complexity of surfaces? Well, Tiger and Kleiner's proof is based on approximating surfaces in the Heisenberg group by planes. If you have a map from the Heisenberg group to L1, you can break that down into a bunch of coordinate functions, and then you can look at the sub-level sets of those coordinate functions. That gives you a bunch of surfaces. The level sets of those functions form codimension 1 surfaces. And Tiger and Kleiner show that if those level sets are sufficiently flat, if those level sets are sufficiently close to planes, then that Lipschitz map cannot be a bi-Lipschitz map. So these arguments about complexity apply because these methods let you decompose these level sets into uniformly rectifiable pieces and then into Lipschitz graphs. And so you can find sharp quantitative bounds on this failure to embed by doing analysis on Lipschitz graphs in the Heisenberg group and Lipschitz functions in the Heisenberg group. And so this lets us find sharp quantitative bounds on Lipschitz maps from the Heisenberg group to L1. And that has a bunch of applications. So the original motivation was for a problem in computer science based on something called the Goemon's lineal relaxation. So this relaxation, this is an algorithm for solving the sparsest cut problem where the accuracy of the algorithm, the accuracy of the answer this algorithm provides depends on how well certain metric spaces embed in L1. Basically, the algorithm produces a metric space, and then the accuracy of the answer that the metric that the algorithm provides depends on how well that metric space embeds in L1. We found sharp bounds on how well the Heisenberg group embeds in L1 and used those to show that the integrality gap of this relaxation is at least on the order of root log n. What else? We use this to show a difference between the 3-dimensional Heisenberg group and the 5-dimensional Heisenberg group. The 5-dimensional Heisenberg group is very similar structure to the 3-dimensional Heisenberg group. In fact, the 5-dimensional Heisenberg group is sort of made up of copies of the 3-dimensional Heisenberg group. But surfaces in the two groups can behave very differently, and that leads to different embeddings. So the 3-dimensional Heisenberg group embeds in L1 with distortion on the order of 4th root log r. The higher dimensional Heisenberg groups embed with distortion on the order of root log r. And as a consequence, if you compare the estimates given by the estimate for L1 and the estimates given by the previous theorems about embeddability into L2, it's different. The 3-dimensional Heisenberg group embeds in L1 with distortion on the order of 4th root log r, but it embeds in L2 in Hilbert space with distortion on the order of square root log r. It embeds better in L1 than it embeds in L2. And that lets us construct a metric space that's based on the 3-dimensional Heisenberg group that embeds by Lipschitzly into L1 and L4, but not into any LP space in between. So there's a theorem of Kadets and Pelczynski that if a Banach space embeds in LP and LQ, then it also embeds in any metrics in any Banach space in between. This says that doesn't work for metric spaces. You have a metric space that embeds in L1 and L4, but not in any of the LPs in between. So yeah, so that's pretty much all I wanted to say. I just want to show you one more picture because I said briefly that one of the reasons behind these theorems is that that surfaces in the 3-dimensional Heisenberg group can be more complicated than surfaces in the higher dimensional Heisenberg groups. And so let me just show you one example, two examples. So these are two Lipschitz graphs in the 3-dimensional Heisenberg group, which get close to some of these complexity bounds. So surfaces, one of the, I guess the takeaway from this is that surfaces in the Heisenberg group can be more complicated than surfaces in Euclidean space, and these are some examples. Okay. Thank you.
Thank you very much. I think we have time for some questions, and I invite on-site audience to ask questions. The only thing, Robert, you would need to repeat questions. So how is it? We no longer have video. So in the green room, I no longer see the video from the from Copenhagen. Oh, they switched it off. Okay, that's too bad. Maybe next time we should tell them not to do it. But well, unfortunately, we no longer have a feed. And with this, I finish this part of the session, and we'll be waiting for you in room 3 in 15 minutes. Thank you.